Sound's not on. Okay. All right. So welcome back, everyone. If you hopefully you can all hear me. If you can't hear me, say something in the chat. But I guess if you can't hear me, then you didn't hear that. Okay. Yeah. No, I had some audio issues this morning, so hopefully it's all okay. So let's see. So where were we, right? So we were looking at code generation and how to lay out objects, or how to lay out Java and Juice data in memory. And then we specifically got to objects. And sort of the key problem that has to motivate our design of the memory layout is this issue of subtyping. Where at the compiler level, we know only the static type of an expression or of a variable, but that variable at runtime could hold objects that are assignable to that type. And so when we're deciding how to implement or how to lay out an object of type S in memory, we have to be able to still access that object if all we know about it is that it's a T or it's something of type T. And so then the key idea is that whenever we're talking about the layout of an object S, it's going to be an extension of the layout of any other type T to which we can assign an S. At least, as much as we possibly can. And we're going to see that there's some cases where we can't actually achieve this, right? So we'll see that later on today. Okay, but for the most part, when I'm trying to design the layout of an object, I'm going to make a prefix of that layout be the design of any superclass of that object. And then over here, I talked about the fact that we have data per object, and each object has some information about its runtime type, the dynamic type, and that's a pointer to its per class data. And so this idea about the prefix goes for both the per object data and the per class data. Okay, and at the end of last class, I promised you I'd give a concrete example. So let me erase a bunch of stuff and do an example. All right, and I'll try and keep this. Well, eventually I'll have to erase everything, but I'll try to keep this idea on here. Okay, so let's say in our Juice program we have a class A, and it has a field, right? So we'll call it FA, right? So this is a field that is declared in class A. All right, and over here I'm going to have an object. It can be a bit smaller. So, all right. So this is going to be an object, and I'll call it object little a, but it's an object whose runtime type is big A. It's an object of this class A. And I'm going to reserve. So these are two words in memory. And I'm going to reserve that first word for something that we'll see in just a bit. And I'm going to decide that the value of the field FA of that object is going to be at offset 4 from the beginning of the object. All right. And then, let's say we finish this class A, and I'll have a class B that extends A. All right. And I'll have a field FB in there. And so the point is that there's places where I could have a variable of type A, but I could have an object of class B in it because class B extends A. And so, how do I design an object of class B? So if I have an object B, little b of class big B, I want to lay it out so that a prefix of it is the same layout as an object of class A. So I'll have that reserved field and then the field FA, but now class B has an extra field FB, right? So I'll have FB here at offset 8. All right, so now, because I have this this kind of a layout, I can read. Oops. So what kind of code can I generate to read field FA? I just need an instruction. I'm going to have a move instruction, and into EAX, I'm going to move EAX. EAX plus 4. And dereference it, right? So here I'm assuming that I start out with EAX having the address of some object, either object A or object B. And the point is that because of the layouts, this instruction is going to read field FA of either object, regardless of whether it's object A or object B. Okay, and I get that because I made the super type of B, I made that be a prefix of the layout of objects of class B. All right, so maybe I'm belaboring this a bit too much here, but now I can extend the example. On the other hand, if I'm not, if there's things that are unclear, do ask questions in the chat. All right. Okay, so I have fields. If I want to access field FB, well, I can only see field FB if my static type is actually B, right? So it's not a problem that field FB is at, is not present in objects of class A, because if I have at the juice level a variable of static type A, accessing field FB on that variable is not allowed by the static type system. Okay, it's only the other way around, right? If I have class B, I can access field FA. All right, so to expand on this, what about methods and what happens with methods? So, let's say I add a method. I'm just going to say p dot for public int ma. All right, and I'll have an implementation of that method, and over in class B, I will override that method. So I'll have ma. And I'll override that method, and maybe in class A I'll have another method ma2, and it'll have an implementation here. Okay, I'm gonna erase the idea down here. Okay, and let's say in class B, let's also have a new method, and I'll call it MB for a method that's introduced in class B. And I have methods like this. Okay, and so in the same way that we want to be able to read field FA regardless of whether I have an object of class B or class A, now we want to call the right method, and we want to generate code to call a method, not knowing whether at runtime we're going to have an object of class A or an object of class B. And furthermore, if we call method MA, then if at runtime it's an object of class A, we want this implementation. But if at runtime it's an object of class B, we want this other implementation of method MA. Whereas for method MA2, it's not being overridden in class B. So either way, we want this particular implementation. Okay, so all right, and I've got a question from Felix, and he says, in languages like C++ with multiple inheritance, how would something like this work at runtime? Yeah, so multiple inheritance is going to mess things up. So for now, so for now we're just dealing with single inheritance. In Java, one nice thing is that multiple inheritance is restricted to interfaces, right? So a class can only extend one other class, but a class could implement multiple interfaces, and interfaces cannot have fields. So for Java, we can, at least for fields, we can deal with a single inheritance, right? You can only get fields from a single superclass. But for methods, we're going to have the same issues as in other languages with multiple inheritance. So we'll get there with methods. For now, there's no interfaces involved, and for now, there's only single inheritance. Okay, so we'll look at multiple inheritance. Okay, so I want to be able to find, either this implementation of method MA or this implementation of method MA, and I want to, at compile time, just generate one piece of code to find that method. All right, and so this kind of motivates this per class data, right? So object A and object B needs to know whether they are of class big A or of class big B, because depending on which class they are, I'm going to need to run a different version of method MA, right? So this is why I reserved this first this first word of each object, and I reserved it as a pointer to the class information. So I'm going to have a separate data structure for class A, and all the other objects of sort of all the objects of dynamic type big A, their first field is going to point to this single structure for class A, and then in class A, well, I'm going to have a list of pointers to the implementations of all the methods of class A, right? So in this case, it's MA and MA2. I guess make it a bit smaller. All right. And these are going to be pointers to the code. So the pointer here for MA is going to point here, and then the pointer to MA2 is going to point here. All right, and so if I want to call method MA, right, so call MA, and again, I'm going to assume that EAX has the address of the object that I'm calling it on, the receiver. Well, I'm going to have first a move instruction. Well, everything is a move instruction, right? This is x86, like every other instruction is move. Okay, but so I move EAX, I dereference EAX, so I get this address, and this gives me the address of my class. So, sorry, I have no space here, but this gives me the address of my class data structure. And then I'm going to, in that data structure, right, I'm going to read say offset 0. So I'm going to say EAX plus 0 because for different methods, the offset would be different, right? If I wanted to call MA2, it would be EAX plus 4. So that gives me the address of my of the actual code that I want to call. And then, I mean, there's other stuff like pushing the parameters onto the stack and things like that. So we'll look at method calls in more detail later on, and I talked a bit about method calls already on Monday. But so there's other stuff, but at least we know the code of the method that we're calling, and now I can do a call EAX instruction. So here EAX is right. So before we had a call instruction where you were calling a constant address, but you can also call a register, and so this will transfer control to whatever address is in that register EAX. Okay, so that's going to call method MA, and now we want to make sure that if I have this object B, right, it's of class B, and and B extends A, so I should be able to call method MA on it as well. And again, at compile time, I don't know whether I have an object of type A or of type B, and so this same code should work for the object of type B. So so I need that first word of object B to also point to the class information of that object. So this is going to be the information for class B, and then the layout of class B has to obey this whole prefix rule. So I first have to have a pointer to MA to class B's implementation of MA, and then MA2, and now I have the prefix, and then since class B adds a new method MB, I can put that in the class layout after that prefix. Okay, the prefix from the superclass. So and now where should these point? Well, so MA, right? Class B has a different implementation of MA, so I'll point that pointer to this implementation, this overridden version of MA. But class B doesn't override method MA2, so its pointer here can just point to the same place as the MA2 pointer of the superclass. And then finally, MB, of course, goes to the implementation of MB. All right. So, this way, the same code, if I happen to have an object of class B, well, it's going to dereference the class pointer. It's going to get the class data structure because that has the same layout as the superclass data structure. It's going to find MA at the same offset, and then that's going to take it to the correct implementation of that method for the subclass. Okay. Right. And so for private fields, right. So for private fields, you can put private fields after the public fields, right? So private fields are only visible within a class, but not in its subclasses. You could actually just include them in the for private fields. No, wait. So let me go back on that. So for private fields, you do need them in an object of class B because, so for example, here I have method MA2, right? So if class A has a private field, then MA2 could access that private field. And MA2 is inherited in class B. So I could have an object of class B, and I could call MA2 on it, and it would have to be able to access that private field of class B. So private fields, fit in the same way as public fields. I don't have this restriction of so nobody is going to access that private field on an object of statically type B, but that object at runtime still has to have that field in it. So the private aspect of the field is enforced within the type checker, right? It's enforced in earlier stages of the compiler. But at runtime, the object has to have space for that private field. And that space does need to be at a consistent offset. All right. I think the distinction, though, is private methods, right? So private methods don't need to go through this dispatch mechanism, at least for Java. So if I have a private method in a class, then it can only be called from methods directly within that class. And so so it can't be, a private method can't be overridden in a subclass. So I don't have to have this kind of a search for the implementation of that private method. The compiler, if I have a call to method, let's say MA3 was a private method, there's only one method MA3, there's only one implementation. So this call, I don't have to compute an address at runtime. The compiler could, at compile time, figure out, label the place where it puts the code of that private method, and then just do a call directly to that label. So that's that call address is going to be a compile time constant. The difference here is that you're calling method MA, but calling method MA means different things on objects of different classes. Okay, so for private fields, things can be significantly simpler. Okay, right. So so there's some nice things about this setup. So first of all, runtime efficiency, right? So reading a field is just a single instruction here. Finding a method, well, there's two move instructions, but it's about as efficient as it could possibly be. And even in terms of space, right? Class B inherits this method MA, but in terms of the generated code, you only generate the body of MA once. Sorry, it doesn't inherit. It overrides MA. It inherits MA2. So you only generate the body of MA2 once, but then you can have multiple classes and subclasses sort of both pointing to that same code. All right. So it's kind of a nice setup. And so everything's nice and happy, and then things break down, right? And we've already had the question about multiple inheritance, and in Java that means interfaces. But before I get to interfaces, any questions here? Okay. All right. So I have this nice diagram. What can I erase here? Well, how about I just do it down here? So let's say I have an interface A, and it has a method MA. And then I have an interface B, right? And it has a public int MB. Okay, and then I have a class let's say class C, and class C implements A and B. And so, I mean, it needs to have implementations of both methods. Okay, so I have an implementation of MA and an implementation of MB. Oops, that's a curly bracket. Okay, so I have an implementation of both methods, and so there's my little Java program, or my little Juice program. Okay, and so now I decide how I'm going to lay these things out, right? And so I'm deciding on the layout of interface A, and I'm going to design its data structure. And so since MA is the first method, it's going to be at offset 0. And same thing for interface B, it's going to be at offset 0, right? When I first see these interfaces, nobody knows that a class is going to come along and implement both of these interfaces. So I pick offset 0 because that's the first one. But then I go to class C, and I need to design the data structure for class C. And at offset 0, well, it needs to be it needs to have both this as a prefix, both interface A as a prefix and interface B as a prefix. But that's impossible because interface A has a pointer to method MA at offset 0, but interface B has a pointer to method MB at offset 0, right? And you can't have pointers to two different methods in the same memory location, right? So so all of this breaks down, and so that's bad. So it breaks down. And so now, I mean, there's no okay, and so let me add a bit more code, right? So why does this matter? Well, I can create an object of class C, and then I can pass it around to somewhere in the code that has no idea that class C even exists. It just treats it statically as a value of either type A or a value of type B, and then it can call method MA on a value that's statically of type A, and it has to be able to find it by its offset, right? And same thing for interface B. So it has to be able to find this particular implementation of the method, right? And you could have other classes that also implement these interfaces that have different implementations of methods MA and MB. Okay, so the whole prefix idea breaks down. So we can't make a prefix of the layout of C be both A and B at the same time. So we need other solutions, and now there's no super nice clean, efficient solution. And so we're just going to look for general solutions. So what we need to do is at runtime, we need an implementation of a function that's going to, so I'll call it function F, right? And it's a function that's going to take two things as input, C and S, and it's going to return a pointer to an implementation. So here C is the dynamic class of the object that we're calling the function, that we're calling the method on, and C is, well, it's the method signature, right? It's the name MA, plus in Java, because of method overloading, you want the name MA plus the types of any parameters. In this case, there are no parameters, but in general, there's going to be parameters. So the types of the parameters determine which method MA to call as well. So, and in some contexts, this is called a selector. Basically, the sort of the identifier of the name type thing of the method that I want to call. And of course, I is the method implementation, right? So implementation, right? Or the code of the body of the method. Okay, and we need to implement this function to run at runtime because the dynamic class of the object, right? The compiler doesn't know. It's only when the program is running that you know C. The compiler does know the selector, right? This signature. It does know that I have a call to method, say, MA. Okay, and so you need to generate code that will compute such a function or some sort of lookup table. Okay, and so there's all sorts of different ways you could implement this, but kind of framing the problem this way sort of means that okay, you need to just find some implementation of a function like this, right? So I'm going to give you two options that are sort of commonly used in various implementations, and two options. Option one, right? So and option one is the first one that I would suggest in terms of simplicity. So this is called a selector indexed table, or SIT. Okay, so and the idea is I'm going to make a table in memory, and I'm going to have a two-dimensional table. And so across the top, I'm going to have all the classes in my program. So let's say, class C and D and so on. And, down the side, I'm going to have all the selectors. So let's say MA and MB and so on. So these are the selectors, right? So the combinations of names and lists of parameter types. Okay. All right, and so this is just going to be a grid, right, of implementation addresses, and it's like a two-dimensional array. It's kind of what you would expect, and so in each of my class data structures, and I'm going to really abuse my diagram here, and I'm going to say, let's actually make word 0 of each class point to the column of my selector index table. So I'm going to have class A and class B in here as well. So I'm going to have word 0 actually point to a column of this table. So here I'm going to, in class B, I'm going to add a word 0. Okay, so that points to a column of class B. So the point is, from any class data structure, you're going to be able to find the address of a column of this table. So when you have your dynamic class, you can find the column. And then the selector, this is known at compile time. So it's just going to be an offset into this table. Right? So so how is this going to work? So okay, and so for in the class information for class C, I would also have a pointer to okay. if I draw this, it's going to really mess up my diagram. Oh well. I think my diagram's already really messed up. So all right. So in the class information for class C, I'm going to have a pointer to the column here, and of course here these cells in the table are going to have pointers to the implementations of methods MA and MB. All right, so I'm going to go here, right? This points to that implementation, and this points to that implementation. So, all right, so if I have this, I know the diagram has gotten messy, but if I have this this kind of a table, let me change this code to call method MB, right? And now I want to call method MB on an object that's statically of the type of interface B. So so what am I going to do? So I'm going to move. I'm going to have this move instruction here for to get the class information of that object, right? So EAX points to an object. I don't know that object's class, right? It could be class C, or it could be some other class that implements interface B. Then my next line, so in my first line, I have gone from the object to the class. So in my next line, I'm going to really just change the comment in this example. So this is going to take me to my selector index table column. Oops. Okay. Column. All right. So now I'm in that column, and now I need to I need to statically think about what my selector is. It's MB, and that's at offset 4 in every selector index table column. So I'm going to do a third move at EAX plus 4 to get the implementation of MB. Okay, so that's how I would use the selector index table. And so, it's not too bad, right? I can still generate pretty efficient code. And it's pretty simple to implement, right? It's this two-dimensional array. The array is compile time constant, like your compiler can generate this this table, right? So and I've drawn it as a two-dimensional array, but really the columns for each class can be separate. You just need to know their addresses, so you need to give them labels. But for example, if you're compiling each class into a separate output file, each class could have its own column as a list of constant addresses in its own file, and the addresses just have to be at a fixed set of offsets. And again, you can use labels, so you can have the compiler generate labels that the assembler will resolve to the addresses of the method implementations. Okay, so it's fairly simple to generate. It's fairly efficient to use, but there's always a but, right? So and I think I'm going to erase this part. My diagram is toast already. So so what's the downside? Well, so the upside, the running time of a call is a constant time, right? It's like 3 move instructions and a call. And the downside is the space. And I'm going to say the space is O of S times C, where I guess C is the number of classes in my entire program, and S is I'm going to say total number of selectors, and just for emphasis, I'm going to say, in my whole program, right? So, so here, S is sort of the total number of different names of methods in your entire program, okay? And, I mean, if you assume that like most methods have unique names, then, S is sort of linear in the size of your program, and C, of course, is the number of classes, so that's generally linear in the size of your program. So this selector index table is going to take quadratic space, right? A quadratic amount of memory to be able to resolve interface method calls. Okay, and Yashin has a question. So if the class points to its column, does it still need the methods in the class diagram? Okay, yes. So yeah, so this is a good question. Sorry, and I'll stand over here so I'm not blocking things. Yeah. So if you have the selector index table, then the class data structure doesn't need to have that prefix in those methods that were class methods, that were not interface methods. So you could use the selector index table for all methods, not only for interface methods, right? So for methods that are in an interface, right? So methods that are ever mentioned in an interface need a slot and offset in the selector index table. But this is a general data structure that could be used for all methods in the program. So you could just implement one selector index table and use it for methods that have nothing to do with interfaces at all. And it would be like one data structure that, and then, one piece of code where it's always the same code that you generate. Okay, so, and that's a fine choice. And for simplicity, you could do it that way. And, I mean, if the goal of the course is to, complete assignment 5 in time and pass all the test cases and get it working as simply as possible, this is a reasonable way to do it. So feel free to do it that way, to use the selector index table for everything, and, mention the trade-offs in your assignment 5 document. It's a solution that like most people don't like because of this quadratic space thing. So the sort of counterpoint is that for single inheritance, where you have methods that are only in classes and not in interfaces, you don't have to do it this way. You don't need this quadratic space. And for those methods, there's a more efficient way. And so, most groups do try to implement that more efficient way, that more space-efficient approach for methods that are not in interfaces. And so in that case, your quadratic part here, instead of total number of selectors, it goes down to only the selectors that are in interfaces, right? And, in most Java programs, there tends to be a lot more classes than there are interfaces. So hopefully this cuts down on a lot of the space requirements. Of course, in theory, it's still quadratic, but it improves the space efficiency of this a bit. Okay, and of course, in a real Java compiler, right, where you have to compile programs with millions of classes, potentially, right? A million squared is gets to be a lot, right? So, okay, and Felix, would it also work to have a part of the class C be the implementation of A. And whenever we cast or assign C to A, we offset the pointer by that offset. So, okay. So, so yes, there are other ways that you could implement this. I think this is a fairly complicated implementation, but it would basically boil down to an extra level of indirection where the selectors in this column wouldn't be individual methods, but sort of pointers to yet another table with groups of methods that would be, the methods of A implemented in C, and then a separate structure with the methods of B implemented in C. So yes, so that's another way of implementing it. And I think that's probably, Felix, I think that's a common approach in many C++ implementations. I don't know if that's what your idea was inspired by, but that's a common way of doing it in C++ implementations. Okay. And if you have sort of more questions or comments on that approach, feel free to comment again. But in terms of the space issues here, back when Java was sort of new, kind of the first, say, 10 years of Java, lots of people did all sorts of research on ways to reduce these space issues, right? So things like sharing offsets between different selectors. The point is, this table, it's quadratic size, but most of the entries are empty because, say class D maybe doesn't have methods MA and MB. So, most of these entries would be null. And so you could try to compress the table in various ways. And, there was a bunch of people that did their PhDs on, how do I compress these tables? Or, another even, crazy approach would be to take part of the space that is unused and give it to the garbage collector and say, hey, feel free to give this out as memory for use in allocating objects. So there's all sorts of tricks that you can use to reduce the space. I want to give a second option, which is sort of an alternative. I would say a potential alternative that you could implement in your compiler. So will the selector index table work if you can dynamically load classes into the program? So if you could dynamically, it should be possible, but it's going to take some messing around. So you have this idea of selectors, right? And you need to know all the selectors that you have. So before you load a class, you're going to need to load all the interfaces that it extends. And as part of loading an interface, you might need to extend the selector index table with new offsets for those interfaces. And then the problem is going to be that that the offset for a selector sort of gets decided at the time that you load the interface. And so that means you're going to have to do a little bit of patching up. So adding, deciding the offsets when you load the interface. And that means if a class extends the interface, then you're going to need to create the column for that class after you've loaded the interface and the offsets only at runtime. So I guess to go back to the question, right, dynamically loading classes into the program, you can dynamically load the class, but you would need to create the selector index table column at runtime, so you wouldn't be able to embed that column into the dynamic into the class that you're loading dynamically, but you'd have to create it at runtime. And I think you'd also have to patch up the calls within the class, right? Because the calls are going to have offsets and okay, dynamically loading, right? So if there's in the class that you load, if you can't hard code the offset into that code, you have to have the selector in there, and then when you load the class, that's when you can translate the selector to an actual offset in the selector index table, right? Because the offsets are being decided at class loading time. So yes, it works with the Java dynamic class loading model, but it's pretty messy and complicated, right? And it wouldn't work with the sort of juice model of I'm going to actually generate machine language, right? So with Java, when you dynamically load a class, you're loading Java bytecode. You're not loading machine language, and so you have some wiggle room there in that the Java bytecode has the selector in it. It doesn't have a fixed offset. But for Juice, you're generating assembly language code, and typically you would want the fixed offsets already in that assembly language code. Okay. All right. So, okay, so you can compress the table. So I want to give another alternative, but if there's more questions, do feel free to ask them. Option 2. So, I mean, going back to what are we doing? So we need to implement this function that takes pairs of C and S and maps them to addresses, right? So, I mean, what's another way of implementing such a lookup function? Well, it's to use a hash table, right? So, hash table. So we have a class and selector pair, right? And we would hash that, and we would map it to an implementation address I. Okay. If I do this now, my space. How much space am I going to need for that hash table? Well, it's going to be the number of such pairs that are valid implementations. So I'm going to say O of the sum over all the classes of the number of methods in a class, right? So for each class, you're going to have as many selectors as there are methods implemented in that class. So where M of C is number of methods in the class C. Okay, and so this is going to be generally linear in the size of the program. Right? So, I mean, it's basically the total number of methods in the program. So that fixes your space issues. Time, well, is a hash table constant time lookup? I mean, depends on what you do for collisions and I don't know. I'm gonna say almost constant time, right? So the almost there is a weasel word. Now, one thing here is that it's sort of not so much the asymptotic time that is so important here. Even if it is a constant time, it's probably going to be more than these 3 move instructions. So the constant matters here. If your program does a lot of method calls, right? Then even if you have a constant, say 15 instructions instead of 3 instructions, that's going to be potentially a significant slowdown. So again, lots of people did a lot of research on ways to speed these things up with all sorts of caching, right? Typically, if you have a certain location in the program and a specific method call in a program, most of the time it's going to be called on objects of the same type. So if you cache the method that you called last time and you just check, oh, do I have the same class? Okay, if yes, just call the same method implementation as last time. That's going to speed things up a lot in most cases. So again, there's all sorts of tricks to speed up that time constant. But of course, it's more complicated to implement a hash table than to implement a bunch of arrays in your compiler. So I mean, it's a nicer solution. Many Java virtual machines use this approach, use a hash table with some caches on top. For your compiler, you can do this. It's going to be more work than the selector index table. It's going to be nicer and more efficient. This would be one case where I would suggest having a runtime library, right? So last week I talked about sort of the general code generation ideas where you plan your memory layout, then you generate code for your program, and then step 3 was the optional one. Hey, write yourself a little runtime support library, right? And if you go with this approach, you want some implementation of a hash table that you can have the generated code use at runtime. So you probably want to write that implementation of a hash table ahead of time and include it with your compiled code, right? So, and you could even write the hash table implementation, say in C, and then pre-compile it and just take that compiled library and say, okay, my generated code always has to run with this implementation of my hash table. This is as opposed to having your compiler output an implementation of a hash table, right? It's easier to just code that library up ahead of time and bundle it with your generated code. All right. Okay, and there's more issues with object layout. So, so I've given you 2 options. I want to move away from implementing method calls, but we're going to have more things that are kind of related to method calls anyway. They're just different. So, but if there's more questions, that's what the chat is for. But I'm going to move on to a different but related topic, and that's subtype testing, right? And so as you recall from the stuff on type checking, right? So the lectures on type checking a few weeks back, there's various places in Java where you need to be able to test for subtypes at runtime, right? So there was instance of tests, right? So you can write a Java expression that says, I have an object in this variable O, tell me whether its runtime class is a subclass of some specific class that I specify A, right? Or you might have a cast, right? So I have a variable O that holds an object of some type, and I'm going to cast that object to type A. And so the compiler has to generate a test that at runtime is going to see what the actual dynamic type of O is and determine whether it's a subtype of A. And then there was this whole thing about arrays and arrays being covariant and that being unsound, and then that requiring a runtime type check. So if I have an array of fruits and I store an orange into it, I'm going to need a runtime type check to make sure that this array of fruits, doesn't happen to be, maybe an array of apples that I'm not allowed to put an orange into. So these are three places in Java where we need to be able to determine, I have a class and I have its runtime type, and I want to know, is it a subtype of some other type? Okay, so these are the three places where we need to do these checks. So the problem is, how do I generate code to implement one of these checks, right? Maybe just the instance of check as it's kind of the most obvious one, but you use the same code for all of these checks. Okay, so that's my problem. Can I answer this kind of a question? And I need to answer it at runtime because, yes, I know A at compile time, but I don't know the runtime type of O at compile time. So again, if I, so how do I answer this question? So again, if I have single inheritance, there's a nice, simple, efficient method that works. So let's look at that first. So if I have single inheritance, and I'm going to show you this by example. Okay, so let's say I have a superclass A and two subclasses B and C. Okay, and so I'm going to do a depth first search of my inheritance tree. So DFS, right? So I'm going to traverse my inheritance tree of classes, and I'm going to number each class with two numbers, with a starting number and a finishing number, so with an interval. Okay, so basically, this is where I can use my green marker that's not so visible. So I'm going to kind of do a traversal of the tree like this. And the first time I see a node, I'm going to give it a starting number, so 1. So I see A, and then I go to B, and I give it starting number 2. And then I'm done with B, right? Then I would, if B had more subclasses, I would traverse its subclasses. And but then I come back, and I give B a finishing number, let's say 3. And then next I start visiting C, and I give it a number 4 and a finishing number 5. And finally, A gets a finishing number 6. Okay? And so I do this traversal of my inheritance hierarchy at compile time. And so after I've done this, I encode with each class its two numbers, right? So in the generated code, I just have to put these numbers like 2, 3, or 4, 5, or 1, 6. Okay, and then B is a subclass of A if sort of the interval of B, so if the interval of B is contained in the interval of A. Okay, so at runtime, I'm going to have some object. I'm going to look it up, and it's going to say, oh, my interval is 2, 3, and I'm doing an instance of check. Is it an instance of A? And at compile time, I know that the interval for A is 1 to 6, and from 2 to 3 is entirely contained within 1 to 6, and so therefore B, yes, is a subclass of A. So the point is, I can do a subtype check with 2 less than comparisons, right? So very simple and very efficient, right? I only need 2 integers in each class, and I need 2 comparison instructions, 2 less than comparisons to do one of these type checks. All right. So, okay, but this only works for single inheritance, right? Because you need this tree, well, this inheritance hierarchy to be a tree so that you can do this depth first search on it and number the nodes. And of course, in Java, with interfaces, we can have multiple inheritance. Okay. So let me erase the middle and leave this. All right, so what about multiple inheritance? Well, I mean, again, well, with multiple inheritance, one thing you can do is create a binary matrix. And really, it looks a lot like the selector index table, right? And so that's why I left the selector index table on here, right? And so I just create a table with the subtypes and the potential supertypes. Okay, and I just go through, all my classes. I've got A, B, and C, and I've got A, B, and C, and what is there? So A is a subtype of A, B is a subtype of B, and C is a subtype of C, and then both B and C are subtypes of A, and that's it, right? Everything else is X, right? These are not subtypes of each other. Okay, so you can create a binary table like this at compile time, and put it in your generated code, and then inside my object layout, right? So remember before I had the object layout, and it had a pointer to the class information. So just like before, the class had a pointer to the selector index table column, I will similarly put a pointer to the column in this binary subtype testing matrix. Okay, so that way, every class knows its column, and if I want to check, is the class of my object a subtype of, say, type A, then I'm going to take the offset of type A and look it up at that offset in this column. Okay, and so again, this is going to take quadratic space in the number of classes, and therefore quadratic in the size of the program. So yeah, I don't know. I mean, but it's but here, here it's maybe not so bad because every entry is just a single bit, so you can compress them into bit vectors. So it's quadratic space divided by 32. So I guess at least we have a very small constant, but hey, it's still quadratic. And then, all the research about compressing selector index tables can also be applied to compressing these subtype testing tables. And, the various other techniques like hash tables, you can also create hash tables for subtype testing. I think in terms of simplicity and in terms of what to do for your compiler, you don't have to do any of these compression techniques, right? In JUICE programs, we're not going to have millions of classes, so quadratic is okay. But of course, in the real world, you would want to optimize these further. The other thing that will go a long way is to combine these two techniques, right? Again, there tends to be a lot more classes with single inheritance than there are interfaces with multiple inheritance. And so, for subtype testing of, when I'm testing whether O is an instance of A, if A is a class, I can use this tree and this efficient technique, and then I can have this matrix only for supertypes that are interfaces, right? And then I'll I'll reduce the size of this table quite a bit. Okay, feel free to invent other techniques, or either invent or look up, and if you find a technique that you like and you think, oh yeah, I really want to try implementing this. I mean, it's your compiler, and this is your chance to try out techniques and experiment with them. So feel free to do other things. I'm just giving you, I think, the two sort of the simplest possible solutions that will work for your JUICE compiler. Okay, as we can generate the table at compile time, can't we just generate the Boolean value directly? So, well, okay, so you can generate the values in the table at compile time. Okay, so these check marks and X's definitely you generate at compile time. Same thing with these numbers, right? For each class, you can give it an interval at compile time, and you output that interval, or you output this matrix into your generated code. What you don't know at compile time is what the runtime type of, let's say we're doing O instance of A, right? So O here is some variable, and at runtime, that variable O is going to point to some object. Okay, and you don't know, and maybe O is okay. Maybe the A was a okay. I can change my example, right? So let's say it says instance of B, and let's say the static type of variable O is A. So at compile time, you only know that O O's dynamic type is either A or some subclass of A. And at compile time, you don't know whether the actual object is actually a subtype of B. And you will only know that by going to the object and going to its class information, and then right? Then you know whether you get the class A or the class B or the class C. All three of those could be the dynamic type of an expression whose static type is A, because B and C are subtypes. But here the instance of check is saying, am I a B? So that you only know at runtime. So does that answer the question? Yeah. So within the table, yes, definitely, I can create the check marks and the X's at compile time, but knowing which column of the table to look in, I only know that at runtime. Okay, and I've got, well, all right, let's try and do one more topic. I've got a few minutes. Oh, and if there's questions, as always, ask questions. Okay, and this is going to be the final memory layout topic. And after that, we can go to actually generating code. But as I've said several times already, I think, it's the planning the layout that's the key, and then generating the code. I mean, I'll talk about it, but that comes after, right? After you've got your layout all set. So the thing to remember about arrays is that arrays are assignable to object. So in our type system, we had this rule that if I have an array of any type tau, I can assign it to a variable of type object, of static type object. Okay, so for example, I could have an array of a char array, or it could be any type really, and I do a new char 2. Okay. Sorry, I'm trying to write fast and it's not working. Okay, so I create an array, and now, one thing that's nice is that Juice says, oh, you can't do much with an A, and that made the type system easier to implement. But what you can do is you can have a variable of type O, and you can assign A to it, and now you can do all sorts of evil stuff, like call methods on it. So methods of class object. So I can say o.hashcode, and that has to work, right? Even though the object is actually an object of, it's the object is not an object, it's an array, right? And similarly, once it's an O, I can say, is it an instance of, some class B? Okay. So, all right. So the point is, I can take an object, I can take an array, assign it to an object type. So, going back to our original idea, so a prefix of layout of array must be a layout of object, right? So this basically, tells you how you need to lay out an array in memory, so how am I going to, so basically an array has to have all the things that an object would have, right? So an example layout, right, would be, let's say, okay, so here's my array, and I can take the first word, and it's going to be a pointer to a class. But in this case, it's not going to be, a class, but really a character array. You can think of a character array type as being like a class, and then you're going to need to have all the same information that you would normally have for a class, but for each different type of array. Okay, and so, I might have a pointer to my selector index table column. Okay, and so you would need a selector index table column for a character array class, and maybe because arrays also implement a few interfaces, and a pointer to the subtype testing table column. So subtype. I'm just going to say subtype column. Right, and then the various methods of object, right? So hash code, okay, hash code, and equals, right? And whatever methods object has, they have to be in the class information for an array type. Okay, and what about the array itself? Well, obviously you want the elements, but before you put the array elements, the one other thing that an array always has is its length, right? So I'm going to say my example here is a character array of 2 characters. So I'm going to have a field of its length, and you want to always be able to find the length of an array. So it has to have the same kind of data structure as an object of some class. In addition, an array has to have a length. And then finally, you can have the elements of the array. So A1, A0 and A1 in this case, it's an array of length 2. And so there you can have, the actual elements. So let's say H and I, right, for an array of characters, H and I high. And finally, so when you're planning the layout of an array, you're really constrained by the layout of objects, because an array has to be able to behave like objects. It needs a length, and then it needs some amount of space for the elements. And typically you put them in order so that you can find the element at a specific index, by doing some calculation on that index. And then finally, one other decision, and this is another design decision that's up to you. In a typical Java implementation, to save memory, you would probably want to make the array elements as small as possible. So in this case, a char is 2 bytes in Java. So you would, for efficiency, you would want to put the array elements, in 2-byte increments. But again, for simplicity and for juice, you could just decide to make all your arrays be 4 bytes increments, right? And waste half the memory. So that's another design decision that's up to you. Okay, so for the class char array, does it have to be specific to this type of array? There's nothing related to char in it. Can we just create a class called array and point all array objects to it? Yeah, well, no, yes, but no. So really, no. Mostly yes, but not entirely. And so the most of this is going to be the same, right? The implementations of all these methods are going to be the implementations that are inherited from objects, from object. So an array cannot override any methods. So this part is going to be the same. The selector index table is also going to be the same, because any interface methods are also the ones that come from object. The one place where you need to be careful is the subtype testing information. And some arrays are subtypes of other arrays, but some are not, right? And so for that, for subtype testing, that information is going to be important. And specifically here, when I have an assignment to an array, right? So I'm assigning an orange, and statically I know that it's an array of fruits. I need my compiler, I need the generated code to be able to look at that fruit array and to be able to tell, is it an array of apples? Is it an array of oranges? Or is it an array of fruits? And use that information about the element type of the array to do the appropriate type test. Okay, so really, well, in the case of a char array, I mean, char is a primitive type, but in general, the array information should also somewhere in here have a pointer to the class information for the element type of the array. So in this case, it would be to char, but for an apples array, it would be to class apple, so that when you try to assign an orange to it, you can do the subtype test. Is an orange a subtype of apple? Okay. Right, so the selector index table doesn't need to distinguish, but for the subtype testing, you are going to need to know at runtime, or need to be able to determine at runtime, the dynamic type of the array. So you do need enough distinguishing information in an array to be able to tell that information. Okay. Potentially another possible design would be to have a single one of these, but to inside your array designate one more field to point not only to the class of that object, but a separate field to the class of the element type of the object. So that could be another potential design. It's sort of, I think most Java implementations do it this way, where they treat each kind of array type as if it was a class, and they create some class information for it. But that would be another alternative, to have a single array class, but then have a designated offset within your array to point to the class of elements of that array. Okay, so if there's more questions, you have a few more seconds to think of questions and ask them in the chat. I'm now done with all of the lectures on laying out objects in memory, and once again, setting that up, preparing it, writing supporting code for, say, accessing arrays or implementing these type tests. That's all important stuff that you need to do before you start generating code. And next week I'm going to talk about generating code for various different kinds of AST nodes. I think you at least broadly did that in CS241, and it might be stuff that you can mostly figure out on your own, but I will talk about that next week. And I'll talk about sort of specific AST nodes, and especially specific AST nodes that are tricky. But for now, there's lots to be working on in terms of the memory layout and supporting code that supports that memory layout. Okay, so any last questions? Okay, I'll stand over here so you can see. All right, so have a good rest of the week and a good weekend. And I'll see you on Monday, and we'll talk about generating code for specific kinds of AST nodes. Okay, bye.